Okay, so merge sort is actually our last example for divide and conquer. And hopefully you've gotten a feel of how divide and conquer algorithms work. Now, to give more of a general discussion with divide and conquer algorithms, you may have noticed that the recurrence relation for these kind of algorithms take on one general form, which is this one. So we have a the recursive call or the recursive running time with n divided by b, where b is the number of partitions. So for example, in merge sort and binary search, since we get two partitions, b will be equal to 2. Then we multiply this by some constant a, which describes the number of the conquered partitions. So for merge sort, since we are sorting both partitions, we conquer two partitions. For binary search, we only need to search in one partition, so that that constant, that a, is equal to 1. Then we have this f of n term, which describes the other operations in the recursive call, which is usually the merge operations. So that is the running time of the merge function for the uh, for the merge sort plus some it's linear plus some constant, and then for binary search it's just a constant. So what since all of the divide and conquer algorithms follow, at least most of them follow this general form, the master theorem tells us that based on the values of a, b, and f of n, we can actually predict or say something about the time complexity without going through the substitution and the recurrence tree. So what it says is, well, what we actually do is compare the big O of f of n with n raised to the log b of a. So usually it's log b since b is the number of partitions. So basically this is the number of conquered algorithms, the log of that to the number of the base of partitions. Hopefully you get that. So uh, we compare these two, and whichever one is greater is usually the time complexity of our recursive function, or if, of our divide and conquer algorithm. So if n to the log b of a is greater, the time complexity is n to the log b of a. If O of f of n is the greater term, then our time complexity is theta of f of n. Then if they are equal, on the other hand, the running time or the time complexity, theta t of n, is n to the log b of a log n. So this is on this is actually the only thing you need to remember, or the only formula you need to remember, since and this term actually is the key term. So it's supposedly not that hard, and it's definitely the easier option when we compare it to the substitution method and the recursion tree method. So if you don't believe me that it works, let's use it to binary search, wherein O of n is a constant, 1, and the our n term is n log base 2 of 1, which is 0, which means which is equal to 1. So since f of n and the n term are equal, we use the case 2 of the master theorem. So the time complexity of binary search is n to the log base 2 of 1 log n. So which results to log of n, which is consistent with our result up here. So hopefully if you encounter more divide and conquer algorithms, or you can actually try the master theorem yourself for merge sort and check if you do arrive at the correct answer. So hopefully you remember this when you need to analyze divide and conquer algorithms in the future. So actually that's it for this week. So good luck with your assessments and good luck with the programming exercise. If you have any questions, just send me an email.